Math 1343, Week 8, Video 4, Calculating the Test Statistic for a Goodness of Fit Test. So far in this series of videos, we've learned how to use the chi-square distribution table. We've learned sort of what a goodness of fit test is in terms of stating its hypotheses to test multiple proportions simultaneously. And we've also learned how to calculate the expected value of the categorical variable for a goodness of fit test. Just a quick reminder, when you're doing a goodness of fit test, you have a claim about multiple populations, in this case the population of sick days on Mondays and Tuesdays and Wednesdays, Thursdays, and Fridays. So you can view it as 5 populations and the percent of sick days that are used on those days of the week. And then we also have our observed data from a sample of 250 sick days and their distribution Monday through Friday. And the basic gist of the goodness of fit test is, does this sample observation deviate from our claim about the population enough to reject it? We'll get all the details ironed out towards the end. Right now we're just building the technique. Also, I still have the days observed values and expected values from the previous video. Just a reminder that in the expected value row, each expected value is just the sample size, which in this case was 250, times the proportion, and more specifically times each individual proportion from the null hypothesis. In this case, it's hypothesized that 25% of sick days were used on Monday, and so 25% times 250 gave us 62.5. But we have yet to calculate the test statistic, and the test statistic follows from calculating the expected values. Now, before we go any further, I do need to add something that I left off of the previous video, and that is, when is it appropriate to use a chi-square distribution to do all this stuff? For example, previously when we were testing means, we needed a sample size of at least 30. When we're testing proportions, then n times p has to be greater than or equal to 10, or 5, depending upon the book you use. Unfortunately, it's inconsistent amongst textbooks. But under what conditions will the chi-square distribution be suitable for doing a goodness of fit test? And the answer is really simple. So, little side note, literally, chi-squared is appropriate to use if each expected value is greater than or equal to 5. I'll be honest, I don't know why 5 is the magic number. I've asked questions like that of statisticians, and the answer I usually get is, well, it just works. As a theoretical mathematician, that drives me crazy. But if you're ever asked, how do you know chi-squared is appropriate to use for this goodness of fit test? The answer is because each of the expected values is at least 5. It's kind of a minor side note, but it is somewhat important. So what is a little bit less minor and possibly more important? Well, calculating the test statistic. Because when we're doing a hypothesis test, whether it's the critical value approach or the p-value approach, we do need a test statistic. A statistic that measures how far off our sample deviates from our claim about the population, and then use the significance level, which we haven't talked about yet, to make a decision about the null hypothesis. So without further ado, here's the formula for the test statistic. The test statistic for a goodness of fit test is, well, it calculates a value of chi-squared, but it's not one we look up from a table. You don't look up test statistics, you calculate test statistics. You look up critical values. The formula is a sum. So we're going to have a capital sigma, and I'll remind you what that means in just a second. Here's what we're going to do for each category. We have 5 categories here: Monday, Tuesday, Wednesday, Thursday, and Friday. For each category, we're going to take what we observed. Well, first off, there's going to be a fraction. And in the numerator, there's going to be a subtraction problem. And the subtraction problem is what we observed, the observed value, minus what we expected. But that difference gets squared. Then that gets compared to the expected value. This fraction is calculated for each category. So we got some number crunching to do. See if I can fit this in this space over here. That will suffice. This fraction is calculated for each category. And just a reminder that this capital sigma means that we're going to find the sum of the results of calculating this fraction for each category. So one by one column by one column, or more specifically, one category at a time, we're going to set up this fraction. Starting with Monday, in the numerator, we're going to have what we observed minus what we expected. So 50 minus 62.5. That difference gets squared, and then divided by what we expected, 62.5. So there's the expression for Monday. And then we do the same thing for the rest of the days of the week. On Tuesday, we observed 50 minus, we expected 37.5. That difference gets squared and is on top of what we expected on Tuesday, 37.5. Then for Wednesday, in the numerator, what we observed was 30 minus what we expected was 37.5. That difference gets squared and then divided by what we expected, which was 37.5. And then for Thursday, in the numerator, what we observed was 40 minus what we expected was 37.5. That gets squared and divided by what we expected, which was 37.5, plus. And then for Friday, where we observed 80, but subtract what we expected, which was 75, square that, and then divide it by what we expected, which was 75. Now, as you can tell, this is a lot of stuff to put into a calculator. Some people will put it in bit by bit and write down a bunch of numbers in between. Some people will attempt to type the whole thing in one fell swoop. The problem with calculating one piece at a time and writing it down is that you start accumulating rounding errors. For example, if I just put this in a calculator and write it down, it's going to be off by a certain amount when I round it to 4 decimal places. Same thing for all of these. Then when I add the 5 results, that error can get compounded by taking the sum of those errors. If you want the most precise answer, you should put it all in the calculator in one fell swoop and press equal. The problem with that is that you have to press a ridiculous number of buttons. So I have a nifty compromise that will lessen the number of buttons you have to press at the end, but maintain accuracy as long as possible. That compromise is to calculate only the numerators first, and then rewrite the expression. So the denominators aren't going to get calculated yet, so I can just write those down. Of course, anytime you recopy something, you're increasing the chance of making what's called a transcription error. I transcribe or I copy something incorrectly. But for the numerators, those are pretty easy to do. Like for the first numerator, 50 minus 62.5 equals, and then square that, get 156.25. And then the same thing for the rest of them. 50 minus 37.5, be sure to complete the subtraction by pressing equals and then pressing the square button, also 156.25. Over here. Now some of these you can do a little bit quicker. I can tell this difference is negative 7.5, but I'm squaring it so the negative doesn't matter. 7.5 squared is 56.25. This difference is 2.5, and 2.5 squared is 6.25. I'm not saying you should do this without a calculator, I'm just saving a little bit of time. And here the difference is just 5. 5 squared, of course, is 25. But by calculating the numerators first, then it's not really that hard to put in the rest of it in one fell swoop. You just have to number divided by number plus number divided by number all the way down. You don't have to worry about parentheses, you don't have to worry about exponents. 156.25 divided by 62.5 plus 156.25 divided by 37.5 plus 56.25 divided by 37.5 plus 6.25 divided by 37.5 plus 25 divided by 75. And you'll get an answer that you'll probably have to round off. This one to 4 decimal places is 8.6667. It's actually 8.6 repeating, but very, very rarely will this come out to be such a clean decimal like that. All right, so we get our test statistic, 8.6667 if we round it off to 4 decimal places. You might be thinking this is kind of a cumbersome calculation, and you would be correct, but it's not really difficult. All you're being asked to do is some subtraction problems, square their answers, and then add up these fractions. So if you break it down in that flow, it's usually pretty easy to get all the way through relatively cleanly. All right, we'll be doing another calculation like this because the last video I plan on doing is a new hypothesis test from beginning to end. But this is the formula for calculating the test statistic for a goodness of fit test. It does require calculating your expected values, which is just the product of the sample size times each proportion from the null hypothesis. I would, if you haven't done so, I would practice putting this in to make sure that you can put it in your calculator correctly. And if for some reason you get an answer different than me, try it again and still get an answer different from me, drop a message in the video below, drop a comment in the video below, and I'll see if I made a mistake.